Hello everyone, today we will talk about piecewise Lagrange interpolation and quadratic splines. And in next video I will consider cubic splines. Let's start with Lagrange interpolation, and more explicitly it will be piecewise Lagrange interpolation. The problem with Lagrange interpolation, as we discussed earlier, it's when you have a lot of points, your interpolation becomes very oscillatory. And to avoid this problem, we can cut our data in some intervals. And for example, we can cut it into 2 points or 3 points, depends on what approximation of Lagrange you want to use. And let's consider an example. You have your points. And what we are doing, we cutting them in pairs. Like this will be the first pair. This one will be the second pair, and so on. I suppose you can see how it goes. And what we are doing, we are saying that now we enumerate each interval as a function of I, and we say that for I interval, we approximate it with a function fi from x, which can be calculated, for example, if we use only 2 points, I plus 1, which will be the right point, minus x divided by times, and here we need to use some notation. Let's just denote fi, it's a value of our function. This will be f1, this will be f2, and so on. And plus x minus xi divided by x plus 1 minus xi times fi plus 1. And similarly, we can build such functions for each interval and then glue them together, and we will get a piecewise function. It will be called piecewise Lagrange interpolation. And you can see that the problem with that interpolation, that our solution is
continuous. Continuous.
No. Our solution is continuous but not smooth. And to get smooth solution, we need another approach. And here comes the splines. Splines, quadratic. The idea of splines, and we can consider quadratic, cubic, and higher order splines, but usually we stop on quadratic or cubic splines, is that we want to have a continuity in first derivative and in second derivative and so on. And to get this continuity, what we are doing, we are actually first solving the equation not for our functions, but for derivatives or for the second derivative. And for quadratic, as the name suggests, we use only first derivative. And our idea is that we want to first interpolate the derivative of our function and then use integration to get our function. And how it goes. Similarly to piecewise Lagrange interpolation, we consider intervals. And for interval I, which from xi to xi, from interval xi to xi plus 1, for example, we want to find function yi of x, but now we consider not our function, but the derivative of our function. And we are saying that it's equal to, well, actually the same relation, but now we need to change to derivative. And later we will show how to find these derivatives. It will be actually our parameters which we need to find in this problem. Fi prime plus x minus xi divided by x plus 1 minus xi fi plus 1 prime. And fi prime and fi plus 1 prime is unknown values, but we will show how to get them. Let's integrate our function yi prime from xi to some x over dx. So integration is simple. what we get is yx minus yxi, and this value we know it's just f of I, so we can say that it's equal to our integrand fi prime of x from xi to x dx is equal to yix minus fi. Okay, and now we need to integrate the right-hand side of our initial equation to the derivative, and let's do it. And we will integrate it from xi to xi plus 1 to simplify our calculations, because later we will substitute in here x is equal to xi plus 1. And making a integration, we will get that it's equal to fi prime plus fi prime plus 1 times xi plus 1 minus xi, and divided by 2. And you need to check this calculation by yourself, because this is a tricky part. However, it's just a linear integral. And now what we are doing, we just equating these two parts, the left-hand side of our integral, and well, when we integrate, we equate the left-hand side to the right-hand side, and what we get is yi at point xi plus 1 minus fi is equal to fi plus 1 prime times xi plus 1 minus xi times at 1/2. And our goal is to find the relation for fi plus 1 prime so that we can use it in the next iteration. And what we get is that this is just fi plus 1, because we need that our interpolant goes exactly through the points which we set. And it will be equal just to fi plus 1 minus fi times 2 divided by x plus 1 minus xi. This is very symmetric. And it's equal to fi prime plus fi plus 1 prime. And now we can find fi plus 1 prime, and this relation is true for every I from 0 to n minus 1. And to start this iteration, we need our f0 prime, and it's usually set by your condition, by condition. For example, you can have that your last derivative is equal to the first, the most left derivative, which is our f0 prime, is equal to the most right derivative, which will be the last one. Or you can make that, for example, f0 prime is equal to f1 prime, or f0 prime is equal to f minus 1 prime, where minus 1 means that it's the last element, or some other conditions. It depends on your choice. And now I want to show you how we can use this representation in our numerical methods, and for that I will use matrix representation, which I told you earlier in my first video. And the matrix representation in that case will be the following: how to build this matrix representation. First, we construct our vector which we are looking for. It's the vector of our derivatives. Then we can look at the right-hand side, and in this relation, it's actually the left-hand side, small joke, and it will be equal to 2 times the vector of relations in the way. Maybe it's better to write it like that one. And now we need to construct our matrix, and it's clear from our relation star that the first row, the condition for f0 is undefined, and then it just once on the diagonal. So here will be 1, 1, then zeros, then it's a two-diagonal matrix with ones on the diagonal. However, we need to be careful how we use this matrix, because for the first row, what we get? 1 times f0 prime plus 1 times f1 prime. And this is the relation for our I is equal to 0. And when we go to the last row, it's actually will be here we contain I from 0 to n minus 1. And here we will have these ones on the diagonal. And here comes the problem, because our second diagonal will cut to the edge, and that's why we need one extra row, actually, where will be set, and the last row is supposed to be, well, everything's supposed to be good with that row, because we also have an extra column here, and we will just go to the corner here. But last row, and also we need, well, here is everything is okay, and we need some last row here. It's our boundary condition. And here, a last row for boundary condition. And you can move actually this row to the top, or maybe in the middle if you want to make your life harder. So, thank you very much. That's all for piecewise Lagrange interpolation and quadratic splines. Let's briefly discuss what we have covered. Let's briefly discuss what we have covered. First, we start with piecewise Lagrange interpolation, and we say that we can use intervals to cut our data to have less order of polynomial in Lagrange interpolation, and then we just glue these functions and get a continuous solution. And we don't satisfied by this solution because it's not continuous in derivative. And what we suggest is to use splines. And the idea of splines is that we want to have continuous derivatives or high order derivative. And in quadratic, as the name suggests, we use that our first derivative is continuous. And how are we doing that? We say that our derivatives, we just use Lagrange piecewise interpolation. We interpolate our derivatives, and then when we glue them, we will get a continuous function. Therefore, our initial function will be order of smoothity 1. And then we calculate the integral of the left-hand side, and on the right-hand side, we equate them and get a relation for the derivatives. And we use the derivatives as a parameter of our problem, and what we left with is we need to set some condition on our first derivative, and then we can solve it numerically or by hands, just by solving this matrix or by solving exactly this relation. Thank you very much. See you later. Черт. Вот никогда нельзя интегрировать у доски. Золотое правило. Так, у меня косяк. Короче, вот здесь ошибка, здесь должно быть не так. Здесь вот эта штука, она должна быть как бы вот здесь. Здесь придется все приписывать. Выглядит ужасно. Сейчас, там идет видео или что? Ладно, тогда это не проблема.